Good day. So our lecture for today is about the continuous random variables and the normal distribution. So if you notice, I am not actually using a presentation mode because we will need to switch views and windows for this one. So again, our reference book for this one is Premman's Introductory Statistics. So if you remember from our previous discussion, we have two types of variables, the discrete variables and the continuous variables, or rather, discrete random variables and continuous random variables. Now, for the continuous random variables, these take up the values where the values of the outcomes are not or rather can take the values of the outcomes are any point within a certain interval. So an example of a continuous variable or a continuous random variable here is the height of the female students in terms of inches. So if you notice, it doesn't look like it's a continuous random variable because this has been categorized already. So what you can see here is actually uh, the continuous variable, but it was changed into a somewhat like a discrete variable. So you have a category of 60 to 61 inches in height, and then another outcome is 61 to 62. So these are its relative frequency. So if the continuous random variable falls between 60 to 61, so this is it falls under this outcome. So when you graph this, it becomes a histogram. This is actually the histogram presents the discrete random variables when we change this, because the height of the female student is a continuous random variable, but the histogram here is a discrete random variable. So how does it work? Because we categorize the values. If the values falls between 60 to 61, it becomes this category 60 to 61. So it has this relative frequency of 0.18. And this is what we can see, 60 to 61. So that's the 0.18 frequency around here. So that is basically how this histogram was made. So if the value falls between, say, 61 to 62, so they have the relative frequency of 0.034. So it translates to around here. So going around with this one, you get your histogram, which is the discrete random probability distribution. Now, what we wanted here is a continuous probability distribution, because in the first place, the outcomes that we are looking at, the height of the female student but is naturally a continuous random variable. So in order to draw the probability distribution for the continuous variable, we get this discretized discrete probability distribution from the categorized heights. We get the midpoints of each category. So for example, the midpoint of 60 to 61 is 60.5. So these are the points at the midpoint, and then connect the dots. So basically, this line here becomes the continuous probability distribution. So here is your probability distribution curve for the heights of your what is this one? Female students. So for the heights of the female students, so it becomes the look just not at the histogram, but at the line itself. So this is your continuous probability distribution now, which was made from first categorizing your continuous or rather continuous random variables, creating a histogram from the discretized versions, and then getting the midpoints of each and then connecting the dots. So this is now your continuous probability distribution. So some characteristics of the continuous probability distribution is that the probability that x assumes a value in any interval lies in the range of 0 to 1. So again, as a probability, its values can take up any from 0 to 1. And the total probability of all mutually exclusive intervals within x can assume a value of 1.0. Similar to our discrete probability, the total number of outcomes is 1. The total the summation of all probabilities of all possible outcomes is 1. So the probability here, when we look at this continuous probability distribution, the shaded area is the probability. So we have here the curve. So remember, the curve was created by getting the probability distributions here. And now, if we get a certain interval within this probability distribution curve and you get the shaded area or the area between, or rather beneath the curve, this is actually the probability. Let's say the probability of a certain outcome happening between A and B. So the probability is equivalent or equal to the shaded area. So if we take into account all of the possible probabilities, the total shaded area beneath the curve is 1.0 or 100. So if you notice, our curve is actually asymptotic. So because it predicts all possible outcomes. So the total of everything is 100% or 1.0. So let's look at more concrete examples. So here is again the shaded area beneath the curve between a certain values of A. So this is basically outcomes A and B. So between the outcomes A and B, so this is your probability of getting an outcome between A and B. So again, say let's look at our histogram example again from the heights of female students. So if we get the probability distribution, so what's the probability of when we ask a random female student and measure their heights? What's the probability of getting a value of 65 inches to 68 inches? So that probability is actually can be solved by getting the area beneath the curve at the interval 65 to 68. So between 65 and 68 inches, the probability of getting this one is the value of the shaded region. So basically, for continuous probability distribution, the shaded region is actually the value of the probability of getting a certain outcome within that particular area. So here is another look. So what's the probability of getting when we sample a random female student? What's the probability of getting a student with exactly 66.8. So if it is a certain point or an exact single point, the probability becomes 0 because it's not the value of the height of where the position is, but rather it's the value of the curve, or rather the area defined under the curve. But since it's a single point area, so you basically have a probability of 0 for a single value. So that's the thing about continuous probability distribution. Unlike discrete probability distribution where the value won't be 0, the value here, the key point here is to define a certain interval. So if it's in a certain interval, you will get a non-zero probability, even if it's 65, 65.1. So you will get a non-zero probability. But if it's an exact single digit of 66.80 or 66.8, so you will get a zero probability based on the continuous probability distribution, because it's not the height of the curve, but rather the shaded region or area beneath the curve here that matters. And again, the area beneath the curve at a single point. So you will have a very, very thin line, which is still a line, a one-dimensional line. So you have a zero. It's a line, so you have a zero width. So you will have a zero area, so a zero probability. So if we define a certain interval between 65 and 68, it won't become zero. So of course, you will have a shaded region here. So let's look at another example. So here is a distribution of time taken to run a road race. So it's a class of 20 to 25. So these are the classes. So for continuous probability, in order to actually create the probability distribution, if we have the total number of some populations in a certain populations, we usually tend to classify them 0 to 1, 1 to 2, 2 to 3. So here is 20 to 25, 25 to 30, and then create a histogram, get the midpoints of each bar in the histogram, and then connect the dots. And this is now your continuous probability distribution. So here is the frequency density of each value. So this is actually corresponds to the area beneath each curve. So this is for data that the population data, we have the complete population data. So this is how we actually create the curve. However, if we are going to classify or find out information from samples and not the population itself, that is where the normal probability distribution comes in. So the normal probability distribution, it applies to some, again, to cases where the population distribution, because here is the population distribution itself. So this is the total number of outcomes on a certain, not on a single experiment, but it determines the whole population data. But even when we do not know the population, the actual population data, or the data that everything, for example, in experiments, when you do experiments in the laboratory, and we want to know, for example, say if you're doing this on an analysis, so what's the probability of getting a value of, for example, you are titrating a certain acid sample. Let's have that example. So in your general chemistry, remember, you were titrating vinegar to get the actual value, the value, or to analyze it, or to get the value of the acidity in terms of acetic acid, percent acetic acid. So unless the population distribution, we won't ever know the population distribution, because we need to get we basically, in order to do that, you need to exhaust the whole jar of vinegar, and titrate everything in the whole jar of vinegar. So that's basically your population distribution. But we don't really do that. What we are actually doing is just get a small sample, three trials, 3 to 5 trials, and then titrate those trials. And that is why we in actual practice, it's mostly the normal probability distribution that we are using, rather than creating our own probability distribution. Because when we do this, when we want to do the actual probability distribution, we would need to exhaust the whole jar of vinegar in order to actually create this probability distribution curve. So we are just getting a certain sample, and that's enough. And then we apply the normal distribution. This is because why do we just we do what why do we do this? What is our basis that the jar of vinegar follows the normal probability distribution? This applies the law of large numbers. And remember from our previous lectures, the law of large numbers is that you have unlimited number of experiments. The number of outcomes, when you look at this is because we are talking about infinity. If you perform an infinite number of experiments, that means a very, very large amount of experiments or samples or trials, the values that you will get, the outcomes of the values will follow a normal probability distribution, that is a bell-shaped curve. So the normal probability distribution, these are the properties. So of course, like other probability distribution, the total area is 1.0, and this one is symmetric about the mean. So if you look at this one, this is not symmetric, because the number of populations involved here are limited. But if you have infinite number of population, this becomes a symmetric curve. So the curve is symmetric, and the point of symmetry here, the axis of symmetry here is actually the mean. And the two tails of the curve extend indefinitely. So as we said, it's asymptotic. Okay? So here is a normal normal distribution with a mean mu. So this is the population mean, and the standard deviation is sigma. So remember, standard deviation tells us how spread out the data. And the shaded region beneath the curve is 100% or 1.0. Now, take note, again, this curve is asymptotic. So it extends indefinitely, showing us that for a continuous distribution, you have infinite number of outcomes. But remember, for asymptotes, as you go far, 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 far away, infinitely far away from the mean, you will get a very, very small or infinitesimal value or infinitesimal difference, shaded region beneath the curve. So the symmetry of the bell-shaped curve or the normal distribution, so with the mean at the point of the mean, so the mean serves the axis of symmetry. So to the left of the mean, that's 50% of 0.5, and to the right of the mean, the shaded region is 0.5 also. Now this shaded region, so at the extreme ends of the mean, so it's usually around plus minus 3 sigma. When we say plus minus 3 sigma, so sigma again is the standard deviation. So how do we apply, or what is the practical application of the standard deviation? The standard deviation tells us the value the difference, or how far the next value is from another. So that means, for example, 0, 1, 2, and 3. So if the standard deviation is 1, so this is, if mu is 0, standard deviation is 1. So plus 3 sigma is 1, 2, 3. So 0 plus 3, so this is a point 3. So anyway, what the point here is, at the farther region, so as your points, at points that are far away on both sides of the bell curve, far away from the mu, the shaded region, the area beneath the shaded region becomes very, very small. So that means it's very, very highly unlikely that a certain outcome will become very, very far from the mu. So basically, outlier. So those are that's what this actually graph means. So at at regions far, far, far from the center or the mean, you have a very, very small probability of getting values that are far away from the average or the mean. Now, the difference of the sigma tells us how far apart the values are. So a very, very large standard deviation shows us a flattened curve. So it's a flat curve, so that means as you go far away, the probability is not really diminished. So it flattens. So at a low standard deviation, that means the values of your sample tend to cluster around the mean. So this is your sigma. So again, the sigma tells you the difference between the standard or the average difference between two values, two consecutive values in your standard deviation or distribution. So you have your a low sigma gives you a tall or a really sharp curve, and then it flattens when you have a large sigma values. Now, if the changing the mu or the mean translates, there's a translation at the same standard deviation. When you change the mean, of course, the bell curve, the standard deviation curve, moves to the left or to the right. So that's the translation of the curve. So the mu and the mean gives us the shape of the curve. The mu is actually where the curve is, and the standard deviation tells us how flat the curve is. Now, for a normal distribution, the mu is equal to 0 and the sigma is 1. So it's the standard normal distribution. So it's actually the normal distribution that we usually see. So here is your standard normal distribution. So it doesn't really stand much for any for practical purposes. This is based on since for example, when we titrate, it's not really that we will get a value of 1. But why do we apply standard normal distribution when the standard normal distribution tells us that the mu is 0, the population average must be 0. So basically, this is just a reference point. So we are using the standard normal distribution as a reference point for our values of whatever experimental outcomes that we might have. So in order to actually define areas beneath the curve, we need to be able to define units on the x-axis of the curve, and that's actually the z. So the z values or the z-scores, these are the units marks on the horizontal axis of the standard normal curve and denoted by z. So this is the z values or z-score. So a specific value of z gives a distance between the mean and the point represented by z in terms of the standard deviation. So here is the area given. So we have actually from our book, the appendix B. So this is in table 4. So I already opened the book. This is actually table 4. So this is the standard normal distribution table. So it shows us the value to the left of z. So these are the entries. So -3. So these are the values of z and z here. So there is no basically y value denoted here. Here is the x and this is also the x value. For example, -3.45. So this is -3.4 and 5. So -3.45 is here. So that's how you actually read the table of standard normal distribution table. So the area to the left of a certain value given by z. So this is the value in our curve. So when I say negative 35, 3.45, so the area is 0.003. So that's to the left of the z. So let's look at this example. So what's the area under the standard normal curve to the left of z, of the z at 1.95? So going to, actually there's a slide here. So going to the table, it's actually similar to the table that we have. This is positive 1.95. Actually, since we need to look at this value, let's just look at the slide. So at 1.95, because this is 1.95, 1.95. So the area is 0.974. So let's check. 1.9991, wait, 0, 1, 2, 3, 4, 5. Okay. 0 0.1 point, so what's it again? 1.95. 1.95. So we have positive 1.95. So again, denoting the area to the left. So 1.95, 1.9, 0, 1, 2, 3, 4, 5. 0.9744. So similar to this one. Okay? So that's to the left of your curve. So 0.9. So the area from the 1.95 all to the extending to the left of your asymptote, this until infinity, the total area here is 0.9744. And if you are going to look at the area, how about the area under the standard normal curve from negative 2.17 to z is equal to 0? Now you now have your basically areas here that have you have two z values here. So if you look, I'm just gonna jump it. So the value for negative 2.17 from the table, negative 2.17, so 1.7, that's 0.150. And at 0, that's zero point 0.5. So again, the 0 is our midpoint. So the area here is actually from 0 to 2.17. So remember, this table gives us all of the regions to the left. So let me, to better visualize this one, so let's look at this sketch of your standard distribution. So I'm going to create, is it a fill? So let's just change the color. So let's use pink. Okay. And walang fill. I don't want to fill anything. How do you do this? Hence. Okay. So let's look. So to the left of 0. Okay. Masyado maliit. So let's increase my pen size. Pen. No. 9. Okay. Let's too large. I think this one is good enough. So from the 0, this is our z-score. So all to the left. So I'll just color everything. So all to the left of this one. Why is it looking like this one? So again, if we color everything, so let's just say to the pink until to the ends of this one. So that's 0 0.5. So this is equal to 0 0.5. So let's just a smaller width. Spain brush. Okay, much better. Stop sketchy pen. Let's look at the pen. Okay, anyway. So this is equal to, so this here is our 0 0.5. Now, let's change my color. So, different color is green. Okay, so how about the other region, which is negative 2.17. So when we say negative, it's to the left of your this score. So negative 2.17, so it's actually around here. The area in our table of negative 2.17 pertains to this region. So the shaded area from 2.17, so this is the 0, so this is negative 2.17. So let me change back to pencil. Okay. So this is negative, sorry, negative 2.17. 2.17. So this area here is negative 2.7. But what we are actually into is the area between the two of them. So changing back to, let's say, blue. Okay. We are actually involved or interested only in the region, here. So from this part to this one. So basically the area here. So that's 0.5. The area from 0.5, this is the 0.5, and minus the area from 2.17. So this is this one. So the calculation of getting this value is just getting 0.5 minus, this is 0.5, sorry, 0.5 minus negative, minus 0.015. The region, because 0.015 is the region to the left of negative 2.17. So this is now the region under the curve. So let's have another example. So what's the area to the right of 2.32 and another from the area of the left of 1.54. So let's look first at the area to the right of 2.32. So here is your 2.32 and we are looking at the area to the right. Now, our table gives us values to the left. So this is uh, what we are looking for are the values that are not in the graph or not in the table gives us to the left, but we want what is on the right. So we'll just subtract it from the total value of the total region under the curve, which is 1.0. So 1.0 minus 9.18 is 0.112. So we just remove the areas to the left of this one. So 1 minus 0.989. So that's the region, the value of the shaded region to the right. Now, for the values to the next one is area to the left of negative 1.54. So area to the left of negative 1.54 is just basically, we are just gonna consult to the table. So negative 1 point, this is positive 1, negative 1.5, 5, 6, 7, 8, 6, point 618, am I correct? 5, negative 1.54, 0.0618, right, 0.0618. So that is the actual shaded region. So let's look at more examples. So between 1.19 and 2.12, what's the probability of getting a value between 1.19 and 2.12? So these are the z values. So this is 1.19 and this is 2.12. Now, we are looking for the area in between them because again, the probability is the area beneath the curve. So between 1.19 and 2.12, so that's the area beneath the curve between 1.19 and 2.12. So to get this shaded area, again, we need to look at the values. So let me just erase this one first. I don't want to do any fills. So let's remove this pencil layer. Okay, I have a lot of layers. Okay, so let's just get a new one. So let's have a grid and apply. So again, if you have your probability distribution curve, like so. Okay, so if you have, this is our mu is equal to 0. So it's a standard normal probability distribution. So from our value, it is 1.19 and 2.12. So if we define the regions 1.19, so again, change my color. Okay. So this is 1.19, 1.19. So the regions, all of the areas to the left of 1.19 from our table 1.19, 1.19, 0.8830. Am I correct? Yeah, 0.8830. So you have, this is, the value is 0.8830. So that's the area of all the regions, all of the shaded regions here. So that's 0.8830. Now we look at the other value, 2.12. So let's change my color again to pink. Okay, so am I correct? This is 2.12. 2.12. So we have here 2.12. So let's say, for example, this is 2.12. 2.12. So all of the areas or the regions to the left, so there are overlaps, of course, because these are regions to the left of this curve. So this is from here up until you get here. So the value is from our table 2.12, 2.1012, 0.983, correct? 0.983. Okay. So this is 0.983. So this is pertains the region from 2.12 up until to the left. And then this is the region from 1.19 to the left. But we are actually only interested, and let's just use black. We are only interested in this particular spot. Between 1.19 and 2.12. So what is this particular, what's the value of this particular spot? So we get, this is the, from here to here, you get 0.983. And then minus, we don't want the areas here to the left of 1.19. So minus 0.883. And so we will get our values now. So this is actually our probability. So 0.983 minus 83, that's 0.1. So the value that we are looking for between 2.12 and 1.9, that's 0.1 thousand. So basically, that's how you do the distribution curve. Now, this is an important thing you should be careful, because some tables will tell you the z value to the right. So just make sure that read the table properly. So the values here should be to the right. Rather, this is to the left. So all of the values that are given to you are those to the left of your zero. Okay, so notice what I'm talking about. So here is those to the right of, this is another distribution table actually, the student's t distribution table to the right. This one is a different one to the right. The z distribution, this one is to the left. So there are some reference books or some reference tables that you can find out there. So they give you not the distribution to the left, but distribution the values from z up until the right side. Or sometimes it's just from the zero, from the mu to the z. So it's either you add 0.5, or basically you need to add 0.5 if you want to get the whole distribution. So read your table properly and know what the values indicate. So here it says that the table on this page give cumulative under the standard normal curve to the left of z. So it must be to the left of z. So all of the values here is from z up to the left infinity side. Okay, so that's the value. Okay, now there's another example here. So this is between negative 1.56 and 2.31. So let's have our normal distribution curve. So I'll just change into a new one. Okay, so it tells us the value must be 1.56. So we have here's a normal distribution. Okay, so negative 1.56, negative 1. So around here, our z is equal to negative 1.56. So here, and the other value is 2.31. So positive 2.31. So around here. Okay, so this is 2.31. Okay, so we want the value here. Again, from our table, what our table will give us, let me change colors. Green. Okay, let me change colors. Okay, so at 1.56, the value in the table gives us all of the area here. So everything up to infinity. And then for the other table, it's positive 2.31. So between, yeah, greater than 1.56 less than 2.31. So the value is negative 1 point, what is it again? 1.56. 1.565, 1.50, 1.70, 1.5, 0, 1, 2, 3, 4, 5, 6, 0.0594. Am I correct? This is 0.0594. 0.594. Where is it? 1.56, so 0.0594. So you have 0.0594. So the area here is 0. What is it again? Negative 1.56. 0.0594. Okay, and then for the other value, it's 2.31. So again, you want to know the value for 2.31. The data in the table gives us from 2.31 up until the whole values. So this is 0.9, 2.31, 2.31, 2.3, 2.3101, 9896. 9896. So I actually I'm checking because I'm not really that confident that I have a straight eyesight. Anyway, 0.9896. Okay, this is 6. Okay. So what we are looking for is the area between them. So change to blue. Okay. So the area between them is this area. Okay, so you just subtract 0.9896 and 0.0534 to get the area between this one. So this is the area that we are actually looking for. So that's basically knowing the area beneath the curve. So that's actually your probability distribution for that. Okay, how about, I save some example here is greater than negative 0.75. So z greater than 0.75. So that means to the right of negative 0.75. So what is the area to the right of negative 0.75? So I'm just going to use this example here. To the right. So since the data in the table that they give us is again to the left, so to get the ones on the right, just subtract it by 1 because the total area again under the curve is 1.0. So subtract it from 1. Okay, so that is our examples for probability distribution. Now let's look at areas within one standard deviation. So what if our z is symmetrical? So the area is symmetrical within a certain interval, negative 1 to 1. Actually, we're just going to apply again. This is just a similar sample of application between the two intervals. So it's just that you get the values of z as plus minus your 0. So the interval is plus minus a certain sub interval. So that's actually just that one. So find the probabilities for the standard normal curve 0. Probability for between 0 to 5, 9, 6, 7. Actually, it's very similar. So 0 to 5, 6, 7. So this is 0 and this 5, 6, 7. So it's since 0 is also, and although it's the mean, it's the reference point, this is also a value of z. So just how we actually are doing, get the value of 0, that's 0.5, and get the value of from the table 5.67, and then the value here minus the value of 0 here. So get your region here. So it's actually just apply the same way we have been calculating areas, shaded areas beneath the curves of two intervals. So it's actually just extended examples. So I'm just going to jump it around now. So how about standardization of the normal distribution, or rather the standardization of the normal distribution we will be talking on the next part of this lecture.